Welcome to the lecture on fundamentals of MIMO wireless communications. We are currently discussing the signal correlation properties, and we have gone halfway through the derivation of signal correlation. So, we start from the point where we left in the last class. So, we had the expression as in this particular expression, and we started off with the expression here received band pass signal correlation as phi RR of delta t with RT and RT plus delta t, where we expanded each of these expressions and did all multiplications, used the trigonometric identities, following which we collected the like terms, and finally we have the expression where we have half cos omega c delta t along with a certain coefficient and half cos omega c 2 t plus delta t along with a whole set of coefficient. So, we have gathered the terms with t together, and we have also gathered the terms without the t. So, we have these two sets of. So, we have basically four functions with coefficients, of which two are with t and two are without t. So, at this point we will make a very important assumption, and this is a very valid assumption, details of which we may look into later lectures, but as of now we assume that this particular signal R of t is wide sense stationary. We will assume wide sense stationarity for this band pass signal, and that is quite valid, and it is proposed by a particular model known as wide sense stationarity uncorrelated scattering by a famous in a famous paper by Bellow in the 60s. So, we will simply use that result over here and see what do we get. So, if we assume wide sense stationarity, what we are defining over here is phi R R of delta t. So, going by that, this phi R R of delta t, if it is wide sense stationary process, then it will be independent of t and will be dependent only on delta t. So, if we use this particular set, then what we are left with is these functions which are function of t should have the coefficient which is 0. So, if we take that, what we get is from this particular one, we would have E of h I of t h I of t plus delta t is equal to E of h q of t h q of t plus delta t, because if this has to be 0, then this must be equal to this. Secondly, what we have is the other function of time is the sine 2 t plus delta t. So, if it is wide sense stationary, this should have a 0 coefficient, and going by that we are going to have E of h I of t h q of t plus delta t being equal to minus E of h q of t h I of t plus delta t. So, this in this expression we should have minus inside, which was kind of omitted in the previous expression. So, sorry, there is a minus over here. So, if we set this whole equation to 0, we are going to have this plus this equals to 0, or E of h I t h q of t plus delta t is equal to minus of this, then only this whole equation turns out to be 0. So, if we now apply these solutions into this expression, what we will be left with is this first equation. There is a first expression, that means this term has gone to 0 because this is wide sense stationary. Similarly, this term has also gone to 0, and on top of which we have results that h I of t h I t plus delta t is equal to h q of t h q plus HQ t plus delta t. So, with these two being equal, we can use this in the first equation. That means, we are going to use this particular expression in substitute over here. So, we are going to get 2 Hi t plus delta t, because this is equal to this, and this 2 will cancel out with this half. So, we will be left with expected value of Hi of t, Hi of t plus delta t, 2 and half cancels out, cos omega c delta t. So, that is one of the terms that we are going to left with. Now, this term is also going to 0, which gives this is equal to minus of this. So, if we take that and replace it over here, then we are going to get HQ Hi is equal to minus of this term. So, we will be getting 2 times minus of this term. So, we will be getting the minus. So, and again that 2 and this half cancels out, minus E of Hi of t, HQ of t plus delta t with sin omega c delta t. Okay. So, now we have this expression for phi RR of delta t. So, we would have this as okay. This particular expression, we could replace it as autocorrelation of Hi parameterized by delta t cos omega c delta t, minus, similarly we could write the same for this. Now, instead of writing HQ, one way of writing this would be HQ Hi delta t, indicating correlation of HQ with that of Hi. You could also write it Hi HQ, it is a matter of notation. We would be following this notation. So, wherever you are writing these things, you should follow the same way of representing this notation. It is not a uniform notation. In some cases, people would write HQ Hi, some cases you would get it as Hi HQ. So, we would follow this particular notation as used over here. Okay. So, this is phi RR delta t. Okay. So, looking at this expression, or if you would derive the expression for phi HH, you could also get it as phi HH delta t is equal to phi Hi delta t plus j phi HQ Hi delta t, and then we could write phi RR delta t is equal to real part of phi HH delta t e to the power of j 2 pi f c delta t, where 2 pi f c is omega c. So, we have these 3 important expressions which describe the signal correlation. So, through the last expression, what we see is that the signal correlation in the band pass or the pass band can be related to that of the signal in the baseband equivalent through the carrier frequency and the real part of it, just like we have earlier written that R t or S of t is equal to real part of S tilde t e to the power of j 2 pi f c t. So, these expressions are similar, and what we can see is that again translating from passband to baseband and baseband to passband is identical, and hence it is related through this f c and the corresponding functions in baseband or passband. So, we can study the baseband equivalent or the complex envelope, and we could still characterize the channel. So, as of now, what we have over here is the passband correlation function is related to the I component of the baseband correlation function with cos and the cross component. So, there is autocorrelation component, there is a cross correlation component along with the cos omega c delta t and a corresponding sin omega c delta t. So, with these we would now proceed to study this phi hi and phi hi, because they characterize phi because only after only after expanding these components we will be able to completely characterize phi because phi is characterized in terms of phi Okay. So, from this point we proceed with our description of phi So, in order to study phi that means autocorrelation of the complex envelope or the baseband equivalent, we would first begin with the autocorrelation of the I components. So, what we have as hi, if you would remember, it is n C n cos phi n of t. At this point we would iterate the assumptions which we had made earlier, and they were that phi n is uniformly distributed, that means p phi n in the range of 2 pi, that means minus pi to pi. Why this was so? Because phi n had a term amongst others which is f c tau n, and we said that since f c is very high when it is close to gigahertz or few hundreds of megahertz, small changes in tau n would result in big changes in phi. So, we would so it is a reasonable assumption to make phi to be randomly distributed, and we can make the assumption it's uniformly distributed in the range minus pi to pi. We would also make the assumption that phi n and phi m are independent for n not equal to m. Now, this is again part of the assumption that we made Whitesense stationarity, because there is this the full model is Whitesense stationarity uncorrelated scattering, which leads to basically that the Doppler shifts in the different directions or the nth paths are independent of each other. We will try and see them at a later lecture. So, as of now we will use these assumptions which are common and which are fundamental in helping us derive these expressions. So, we try to calculate phi hi delta t, which is equal to expected value of sum of n equals to 1 to capital N C n cos phi n of t times m equals to 1 to n C m cos phi m of t. This is the expression, and again we will follow the same techniques. That means, we will expand it. So, we could write sum over n C m C n phi n of t phi m of t, sorry, it is t plus delta t plus delta t. So, that would be E of, so we have a cos sorry, excuse me, we would write it as C n C m cos phi n of t cos of phi m of t plus delta t. So, we have a cos A and cos B. So, we will expand that, we will have n equals to 1 to n, and we will break it into two parts. So, the first part we will break where m is not equal to n, C m cos phi n t cos phi m t plus delta t, and we have the other part which is sum over n equals to 1 to n and m n equals to m equals to 1 to m C n squared cos phi n of t and phi n of cos t plus delta t. This is cos. So, we have these two terms, we have broken it into two terms for our ease of our steps that which are supposed to take. And if we look at this particular, the first term, if we look at the first term, we have made certain assumptions that phi n and phi n are independent for n not equals to m. So, we have created that set of summation where n is not equal to m, and if they are independent, we have expectation of cos phi n times expectation of this, and if phi n is uniformly distributed between 0 to 2 pi, we can say that cos this whole term, expectation of this term goes to 0 and that term goes to 0. So, this term would finally end up in 0 and we will be left with only the second term. So, if we proceed with the second term, what we are going to have is again this cos of phi n and cos of phi n t plus delta t. So, this could be again broken up into two parts, that means cos of phi n t plus phi n t plus delta t and the one which is the difference. So, when we have that, we will be getting E of sum over n equals 1 to capital N C n squared, and of course, there is this half cos of phi n of t plus phi n t plus delta t plus cos of phi n times delta t, because when we take it out, phi n of t minus phi n of t plus delta t. So, we will be left with this term, and if we look at phi n of delta t, this is 2 pi f d n times delta t. So, that is what will be left in this particular expression. And if you look at this term, which is phi n of t and phi n of t plus delta t, you are left with phi n of 2 t inside this. And again, as we bring the expectation operator inside, this term would be going to 0. So, what will be left with is only this particular term. So, if we take this term, then we could write this as a summation of expected value of C n squared times half times expected value of cos 2 pi. So, for our case, what we have is f max times cos theta n times delta t. If you refer to the earlier expressions of phi n, f d n is basically f max times cos theta n, we are going to get these expressions. Now, we are going to make some important assumptions again, or if we look into the details, so that we are able to derive the expression correctly. One thing we would remember, that sum of C n squared is equal to omega p, and n equals 1 to n equals 1 to capital N. So, if we have the expectation operator on this, so what we would be getting is n times C n squared, expected value of C n squared is equal to omega p, or in other words, expected value of C n squared equals to omega p by n. So, we can say this over here. Now, on this expectation operator, this expectation is to be taken across theta n, and to do that we basically need p of theta n. So, p of theta n is basically probability of the ray or the nth path arriving at a particular theta, and we make again the assumption that means what we are talking about is there is the transmitter, there is the receiver. So, rays keep coming from different directions. This is the first path, the second path, the third path. So, the first path, what is the probability that first path comes to a particular direction? Now, we have been saying that the probability of this ray coming, or the nth path, is 1 by 2 pi is the distribution, and that will be same for all the paths. We do not know whether the first path comes from this direction or that direction, or the second path comes from this particular direction. So, we would say that p theta n is equal to p theta is equal to 1 by 2 pi for all paths, and that would help us in evaluating this particular expression. So, when we take a look at this first part, what we would get is omega p by 2 n, and of course, n is equal to 1 to n, and this expectation operator would still remain expectation operator, but cos 2 pi f max, instead of cos theta n, would write it as cos theta times delta t. So, if we now look at this, this expression is independent of small n, this expression is independent of small n, and this gets n times added. So, we would have n multiplied, and this would result in omega p by 2 times expectation over theta. So, this was expectation over theta n, this was expectation over theta times cos 2 pi f max cos theta times delta t. This is basically phi h I delta t, and we have seen earlier that we have got phi h I delta t is equal to phi h q delta t. So, we have evaluated this, which is equal to this one. We only have to remain to calculate h q, and it is kind of from these derivations you can almost guess what would be the h q. So, phi of h q delta t could be this, you can work it out, would be expectation over theta. Instead of cos, there will be a sine 2 pi f max cos theta delta t. This is kind of clear because the coefficient that you have with this h q is sine omega c delta t. So, I mean that is kind of an indication, but if you derive through the steps you are going to arrive at this. And so, what we have finally is the expression of phi h I delta t and phi h q delta t, which would together help us in defining the expression of phi h delta t, because phi h delta t is in terms of phi h delta t plus j phi h q delta t, and here we have phi h delta t defined and phi h q delta t defined. So, with this we have been able to define phi h delta t. Now, since phi h delta t is defined, we can then define phi r delta t. So, what remains for us to do is to evaluate these expressions for E theta. So, basically this this expectation, if we can work out this expectation over theta, then we have solved the complete expression of phi h. So, if we go ahead and again our comes to our aid is p theta is 1 by 2 pi and theta in the range of minus pi to pi. So, this is basically the 2D isotropic scattering model that is what we are referring to continuously, and since this was first proposed by Clark, we would usually call this the Clark's model. This is how it is well known. That means the probability of rays coming from all directions, that means the probability of rays coming from different directions is uniform. This is very important. So, we just need to remember this is the Clark's model of 2D isotropic scattering. This is a very famous model, and if we follow this and we try to evaluate phi h I delta t, what we get is omega p by 2. That means we are evaluating from this point, and to do this E of theta, we get minus pi to pi cos 2 pi f max cos theta. Now, we have the term that this has to be calculated. So, to calculate this we need to have two things, one is p theta, and also we need to identify what is the gain of the antenna as a function of theta, because sometimes there are directional antennas, sometimes there are omnidirectional antennas. Again, in the 2D isotropic scattering model, we will assume that the gain of the antenna with respect to direction g theta is equal to 1. That means it is the same gain in all directions. So, ideally speaking, we have to have g theta, p theta, d theta. So, this actually gives us a general method of calculating the correlation function. So, we have used we will be using p theta equals to 1 by 2 pi, and we will be using g theta equals to 1 in our case, but this expression could be used for other situations where p theta is not equal to 1 by 2 pi and g theta is not equal to 1. So, from this point the results would be deviating. So, we could get omega p by 2 into p theta being 1 by 2 pi minus pi to pi cos 2 pi f max delta t times cos theta. I have just moved delta t on this side d theta. So, if we look at cos theta, theta has a range of minus pi to pi. So, cos theta has a range of minus 1 to 1 and cos of minus alpha is equal to cos of alpha. So, using this we could also write this as omega p by 2 multiplied by 1 by 2 pi 0 to pi. Because of this we will be integrating only in one range and we would multiply by 2 cos of 2 pi f max delta t cos theta d theta. So, this would cancel out, 2 would cancel out. So, what we have this as omega p by 2 pi integral 0 to pi cos 2 pi f max delta t cos theta d theta. And this could, because again of cos theta being in the range of plus minus 1 and cos of minus alpha being equals to cos of alpha, you could also write this as 0 to pi cos of 2 pi f max delta t sin theta d theta without any change in your expressions. And then this is the well known Bessel function of the 0th order of the first kind f max delta t. So, where j 0 is the 0th order Bessel function of the first kind. So, what we have derived to this point is the autocorrelation function or the phi hi component of delta t, which has come out to be a Bessel function of the first kind of 0th order, and the expression would look like the figure would look like the one we have here. As you can clearly see, this is the x axis, which is indicating in this particular figure. This figure is taken from Stuber. So, this notation for our example we will be having fm delta t on the x axis. So, that is basically normalized, because what we have on the x axis is omega p by 2 j 0 2 pi f max delta t. So, if you look at this expression and we take fm or f max delta t, then we could choose different values over here and we could plot it and they would all map to one figure. So, this x axis is having fm delta t on the x axis. So, that is f max delta t. This is the autocorrelation function which is normalized by omega p by 2. So, that the max value is at 1. So, you could clearly see that what we have in the x axis is just this j 0 function, okay. And this curve is very important, because at certain point you can clearly see that the correlation reaches 0, and from this we will be defining what is known as the coherence time of the signal, that is the time for which the signal is correlated to itself. We stop our discussion at this point and we will continue the next lecture describing what is coherence time, and also we will look at the correlation of HQ and HI components, so that we are able to define the autocorrelation function or the correlation of the received signal, which would help us in understanding or characterizing the channel partially for small scale propagation models. Thank you.